We're back, and today we're continuing to talk about the atomic theory. As you recall, so far we have three models of the atom. We have this Dalton billiard ball model of the atom, where Dalton thought the smallest particle in nature was the atom. Along came J.J. Thomson, and he discovered subatomic particles. We have this positive matrix of protons, and for every proton, there is an equal number of electrons. This became known as the plum pudding model of the atom. And then most recently, we've discussed the Rutherford model of the atom, where we have a tiny dense center where most of the mass of the atom was located. That dense center had a positive charge because it was made up of just protons and neutrons, and then huge distances away from that nucleus, the electrons were buzzing around. And we called this the Rutherford planetary model of the atom. Now today I want to talk about something called the Bohr model. We won't be able to get all the way through the Bohr model in one video, because in order to understand the Bohr model, we need to understand the nature of light. In fact, not just visible light, but all of what we call electromagnetic radiation. Bohr learned something about how the electrons were orbiting the nucleus. So how the electrons orbited the nucleus. And this became a breakthrough in the field of chemistry. It helped us to understand what chemistry was and why certain chemical reactions, in fact, why all chemical reactions occurred. So the Bohr model is a pretty important model when it comes to chemistry. So let's talk a little bit about light. There are two variables that relate to a beam of light. These variables are wavelength, which we will symbolize with the Greek letter lambda. It looks like an upside down Y, and frequency, which is symbolized by the Greek letter nu. It sort of kind of looks like one of those birds you drew when you were a little kid and you drew a flower and a hill and a sun and a cloud and some little birds in the sky. So that's the Greek letter nu. Now the unit of wavelength shouldn't be a surprise. It's a wavelength. And so we use the unit meter for wavelength. The unit of frequency is the unit called hertz, which is cycles per second. Now you may have heard of the unit hertz before. We usually, to begin with, just say cycles per second. In fact, we omit the term cycles just to make the units work properly in just a minute. So the unit we're going to use for frequency will be 1/seconds, or seconds to the negative first. So if frequency is multiplied by wavelength, what unit do we get? Oh, that's not wavelength. Hold on, let me fix that real quick. So frequency is multiplied by wavelength. What unit do we get? Well, let's see. Frequency is 1/seconds, and wavelength, we said, is meters. So we multiply meters by 1/seconds. Don't we get the term, or the unit, meters per second, or lowercase m over lowercase s. And this, kiddos, is a velocity unit. It's a unit of speed. It's how fast something is moving. And of course, all light travels at the same speed. So this ends up being 3.0 times 10 to the 8th meters per second. All light travels at that speed. We call this the speed of light, which is symbolized by the lowercase letter c. So back up here, where we multiplied frequency by wavelength, we end up with the unit meters per second, which we symbolize with the lowercase letter c. All light travels at that speed. That means, kiddos, when this frequency unit gets big, this wavelength unit has to get small. because the product of the two always has to equal the same number, 3.0 times 10 to the 8th meters per second, and vice versa. When the frequency gets small, the wavelength has to get big. So, like I said, this applies not only to visible light, which we see right here, it also applies to all parts of the electromagnetic spectrum. They all travel at the same speed, whether we're dealing with AM radio waves, visible light, or gamma radiation. They all travel at the same constant speed of 3 times 10 to the 8th meters per second. So we are going to relate frequency and wavelength of these different types of electromagnetic radiation to each other. So let's take a look at a few questions. Use the figure above to answer the following questions. What is the approximate wavelength of AM radio waves? So let's see, AM radio waves have a wavelength of about 10 to the 4th meters. Now, kiddos, that's 10,000 meters. What is the wavelength of FM radio waves? Well, let's see, FM radio waves have a wavelength of about 1 meter. Which of those two waves travel faster, AM or FM? Well, if you've been listening, you would know that they travel at the same velocity. Don't they all travel at 3.0 times 10 to the 8th meters per second, the speed of light? Well, if they all travel at the same speed, and one has a much larger wavelength than the other, which has a higher frequency, AM or FM? Well, before I answer that question, I want to give you a silly little metaphor, okay? This metaphor involves a little girl and her day at the beach. Now, the girl has actually a couple of different days at the beach. The first day at the beach, the girl is looking out at the ocean and she's playing in the waves as little kids often do. And in her first day, the waves are huge distances away from each other. So this wave will hit the little girl and it might knock her down. She might be scared for a minute, but then she gets up and sort of thinks that's a little bit of fun. And so she waits for the next wave and lets the next wave hit her. And it might knock her down. And before you know it, she's having a wonderful day at the beach. You'll notice that when she's having a great day at the beach, this wavelength is huge. There's a big wavelength. As a result, the frequency at which she's being hit by those waves is small. So a big wavelength and a small frequency. The energy that's being inflicted on that girl is also small. She's not being hit very often. She's really enjoying her day at the beach because the frequency is small and the distance between waves, so this wave peak to this next wave peak, is huge. It takes several minutes for each wave to come to the beach. Now, let's say she goes to the beach the next day. So here she is. She had such a fun time the first day. She wants to do the same thing the next day. But this time, the waves are really close to each other. So this time, the wavelength, the distance between waves, kiddos, is really, really small. So she gets hit by a wave and gets knocked over, and before she can get up, she's hit by the next wave, which knocks her down again, and before she can even think about it, she's hit by the next wave and the next wave and the next wave, and before you know it, she's crying. It's just a bad day at the beach. She's screaming. Fortunately, her mom and dad are nearby. They see what's going on. They grab her and they pull her away from the waves, and everything's fine at the end. But why was it so miserable the second day? Well, the wavelength was small. So tell me about the frequency. Yeah, the frequency was huge. She was being hit every few seconds by a wave. Tell me about the energy. Yeah, the energy was also huge. When the distance between waves are small, both the frequency and the energy increase. So let's go back to our AM and FM radio waves. Which has the higher frequency? Let's see, AM waves have a wavelength of 10,000 meters. FM are only a meter. So won't the FM waves be hitting her more frequently? Yeah, so FM has the higher frequency. Which waves have the higher energy? That's right again, FM. So when you do these types of problems, and when you think about electromagnetic radiation, I would encourage you to think about our little girl at the beach. And remember, when the wavelength is big, the frequency is small and the energy is small. When the wavelength is small, the frequency is big and the energy is big. Okay? That's good enough for now in our first video. We're going to practice this again with our next video several times. So stay tuned. See you soon. Bye-bye.